Many military enthusiasts ask, is a 36 megajoule railgun possible in a Trump-class battleship? The concept sounds amazing on paper. You build a massive modern surface combatant and arm it with a giant cannon that uses electromagnetism instead of gunpowder to shoot a metal block at Mach 7. According to historical archives, a 36 megajoule weapon was intended to strike land targets over 100 nautical miles away. However, when we look beneath the hype at the actual engineering documents, we find that deploying a massive 36 megajoule railgun on a warship is blocked by a severe wall of materials science that current technology cannot easily bypass. The main reason we do not see these giant weapons on active warships today is because of rapid rail degradation. To launch a projectile with a massive 36 megajoules of energy, you must force millions of amperes of electricity through parallel copper rails in a microsecond. This creates extreme plasma erosion, cracking, and structural warping inside the barrel. While land-based prototypes by BAE Systems and General Atomics fired hundreds of times during laboratory development, the internal rails degraded so quickly that they required constant, complex maintenance, making a 36 megajoule weapon highly unreliable for the continuous firing needed in a real naval battle.
Because of these persistent material failures, a combat-ready 36 megajoule railgun will not be achievable for deployment within the 2030 timeframe. The U.S. Navy recognized this technical bottleneck after spending over $500 million and officially paused funding for its main EMRG program to focus on hypersonic missiles instead. Inventing synthetic alloys that can conduct massive electricity while resisting structural cracking takes decades of laboratory research. Expecting a 36 megajoule main cannon to be ready for sustained wartime operations by 2030 is simply unrealistic because the basic industrial engineering is not there yet. While the United States struggled and failed with the high-energy 36 megajoule dream, Japan took a completely different, highly pragmatic path. Led by the Acquisition, Technology and Logistics Agency, ATLA, Japan chose to scale down expectations and focus heavily on lower energy limits, specifically around a 5 megajoule system. By lowering the power, Japanese engineers made a massive breakthrough in managing barrel wear and heat. This allowed them to move the tech out of the lab and onto a real warship, conducting successful world-first offshore firing trials from the naval vessel JS Asuka.
Instead of forcing an unstable 36 megajoule weapon into reality, the modern solution lies in a high-low naval doctrine. Under this framework, the Trump-class battleship is reimagined not as a traditional heavy gunship, but as a massive high-tier capital ship powered by nuclear propulsion. By utilizing a nuclear reactor, the battleship gains unlimited operational range and an enormous self-sustaining electrical grid. This endless supply of nuclear power easily recharges the ship's internal capacitor banks, allowing the single forward 5 megajoule railgun to operate at its absolute maximum efficiency without draining the ship's primary propulsion systems. With a nuclear backbone, the true role of the Trump-class battleship shifts from a direct brawler to a massive command ship for unmanned networks. The battleship serves as the floating brain of the fleet, controlling a distributed network of unmanned surface vessels and large unmanned surface vessels. These low-cost, expendable drone ships sail far ahead of the battleship into dangerous waters, carrying extra missile cells, radar scouts, and anti-submarine sensors. This protects the multi-billion-dollar nuclear capital ship from being ambushed, using the low tier to extend the eyes and ears of the high-tier command hub.
Operating within this unmanned network, the single forward 5 megajoule railgun turret offers a massive financial advantage in long-term logistics. Standard defensive missiles used to protect modern warships are highly complex, carrying expensive tracking sensors and explosives that cost between $400,000 to over $1 million per shot. In contrast, Japan's proven 5 megajoule railgun projectile is a basic solid piece of tungsten costing around $25,000. Mathematically, using the 5 megajoule railgun to swat down cheap enemy drone swarms or cruise missiles that slip past the forward USV screen keeps the capital ship safe without emptying its limited and expensive VLS missile inventory. Technically, Japan's ATLA 5 megajoule railgun was never designed as a long-range strategic cannon. It fires a small 320-gram slug at Mach 6.5, built strictly as a short-range point defense weapon. Against fighter jets, it is only effective in strict head-on scenarios because the unguided slug gives an agile pilot past 20 kilometers enough time to maneuver and break the intercept. Its true strength lies in killing hypersonic cruise missiles that fly straight toward the ship on predictable sea-skimming paths. At 20 to 30 kilometers, the Kinetic slug meets the missile head-on at Mach 3, using combined impact energy to destroy it. To improve these odds, Japan is researching smart projectiles, although the internal electronics must somehow survive a violent 30,000 Gs of launch acceleration.
However, against ballistic missiles and hypersonic glide vehicles, the 5 megajoule railgun is simply not realistic. Because an HGV maneuvers unpredictably at extreme speeds, an unguided railgun slug cannot be steered to chase it, especially since the blinding plasma sheath forming around the flying projectile blocks all GPS or radio correction signals. That is why the United States and Japan are not relying on guns for this threat, choosing instead to jointly develop the Glide Phase Interceptor to destroy HGVs in the upper atmosphere. Ultimately, the 5 megajoule railgun serves as an outstanding close-in shield for cruise missiles and drones, leaving the high-altitude, weaving hypersonic threats firmly in the domain of heavy VLS interceptors like the GPI.